last time we tried to calculate the energy corrections from electron-phonon coupling, and this energy corrections contributed from these two diagrams as we mentioned last time. And by second order perturbation, assuming that the electron-phonon coupling is a weak perturbation, and by summing over these two terms that we are able to derive such expressions by taking the expression value of this second order term, and we will get both the Fermi function and also the Bose vector, okay, because we have both fermions and bosons, and electrons are fermions, but there's a boson, so-called propagator here, right? As a result, we could have such a multiplication or product of a Bose vector and a Fermi function. Okay, so if you simplify these terms that we mentioned last time, you should be able to derive such a vector. And I leave this to you as a homework exercise. Start from the second order perturbation theory and simplify all these diagrams that we just mentioned. And then you take the expression value of that second order term, and you could derive such expressions. So I believe the first term corresponds to this first diagram, the second term from the second diagram. Okay, so that's the straightforward calculation. So let's just start from here and manipulate this term a little bit further by adding the subtraction the term, which will go to 0, and that term is called delta. So you can show that I could rearrange this term in such a way that I can add a term delta, which is defined here, and you can show that this delta term vanishes because this is the odd function in k. If you exchange k and k prime, and this term get a minus sign. So, but you need both to sum over both k and k prime. So when you sum over both k and k prime, it doesn't matter which term that you sum first. So you could interchange this k and k prime freely. So when you do so, you find that this delta goes to minus delta, and therefore, when you sum over both k and k prime, this vanishes. Okay, so you add and subtract a term which vanish. It doesn't matter. Okay, but the advantage play this game is to actually come up with some terms which could be easily understood and interpreted. Okay, so after you play this game, you forget about this delta, but when you add this delta term inside this bracket, you can organize this term into these two new terms. If you look at these two terms, you immediately see that, well, the first term involves this Bose vector that I just mentioned. Okay, but the second term, it doesn't depend on the Bose vector. It depends only on the Fermi function. Okay, but of course, there's an overall Fermi functions multiplied outside of the bracket, but we will interpret these two terms in a different way later. Okay, so this is the general formulation of this corrected eigen energies in this electron-phonon coupling present in your Hamiltonian, and this epsilon 0 is the energy of a free electrons and free phonon. Remember that. Okay, so this epsilon 2 is the second term here, which is proportional to this second order in electron-phonon coupling constant m squared multiplied by all these complicated terms. But you can see very clearly that from this new eigen energy, epsilon 2, and this term will actually change both the phonon energy and electron energy. So because it depends both on the, we'll see just a moment, okay? It depends on, both the electron occupation and K, or Fermi function. It also depends on this boson occupation number. Remember, when you define your quasi-particle excitation energy, say in the Hartree-Fock chapter, so we have encountered such a definition where the total energy of the system, say in the Hartree-Fock Hamiltonian, and if you take this derivative of this Hartree-Fock energy with respect to this occupation for electron, then you get the Hartree-Fock corrected electron energy, right? Okay. So in a similar way, here we first calculate the phonon energy change, which is defined as the derivative of the total energy with respect to this phonon, say, occupation number, because this is the, suppose this is the phonon corrected energy, and this should be, say, proportional to occupation times h bar omega q theta, right? And this is nothing but b dagger b, right? You sum over q. Okay, so which means that you need to differentiate this energy with respect to this occupation to get a new phonon energy or frequency. So the first term that will contribute to this phonon energy is the epsilon 0, because this contains this free phonon kinetic energy and also free electron, but it doesn't matter for the electron parts, but if you take a differentiation of the free phonon energies back to this phonon occupation, you get nothing but the free phonon energy, right? So this is just a free phonon energy. But the second term is the term that we pay attention to more closely, because the second term comes from this epsilon 2, right? Which comes from this second order energy corrections. And it also depends on this NQ, right? And especially the first term. So you could actually take a differentiation of this epsilon 2 with respect to the NQ occupation, and you collect the remaining part, and this is precisely the term that will change the phonon frequency or energy. Okay, so this is the second term with a minus sign, which will change the phonon frequency. Okay, so we will analyze this term in just a moment, and we will see that this term will lead to a singularity near the Fermi momentum, so-called CoAnomaly. And let's just look at this phenomenon. So let's look at the derivative of this new phonon frequency, which includes the contributions from the electron-phonon coupling. And let's look at how it looks like near the Fermi momentum. So let's take the derivative of this new phonon frequency with respect to this variable called q star, and which we will see in just a moment what this q star is. But let's just take the derivative. And if you take the derivative, and remember that this epsilon k minus q is the free electron kinetic energy at a momentum k minus q. This is for electron. So later we will see something singular happens when q star is very close to 2kF. Remember, this q or q star is the momentum transfer between the incoming and outgoing electron states, k minus k prime. So we'll see in just a moment that if we keep organizing and cleaning up this term, we will see that this q star will make this derivative singular at particular q star, which is 2kF. So let's just check. So we could organize this term. So let me just try to clean up this. So you could very easily take the derivative of this electron kinetic energy and with respect to this q star, and then you get this k minus q star after you taking the derivative. Then you could simplify this even further. K minus q star minus k. Of course, this q should go to the particular momentum transfer q star. Then you could reorganize this thing, everything square, right? So this is everything square. Okay, so you can take the leading order term. So let me write it here. K minus q star square times 2k minus q star squared. Because both k and k prime are very close to the Fermi surface, and I could just express everything in terms of this k, because this k prime is gone. We only sum over just a single momentum electron state k. But we know that in the zero temperature limit, this k is very close to the Fermi momentum. So there's a k and plus k here. So this is 2k minus q star. And this k subtract from k, you get 0. But there's a minus q star here. And then we should square this. So this is the final expression. So you can very clearly see that when k is very close to kf, and q star will make this term singular when q star goes to 2kf. And this derivative actually goes to infinity. All right, because this, when q star is actually 2k, and when k is very close to kf, so q star is 2kf, and which makes this denominator vanish. Okay, very singular term in the denominator, which will make this term very singular, and this is called 2kf scattering. And this phenomenon is called the CoAnomaly, which means that the phonon momentum, which is the momentum transfer between these two electrons when they interact with phonon, and when this momentum transfer q goes to 2kf, then this phonon frequency, the new phonon frequency, becomes infinity. And this phenomena is called the CoAnomaly. Okay, so let's take a short break, and when we come back, we will emphasize this derivative at 2kf one more time, and then we will comment on the connection to the experiments. And this is the real phenomena that could be detected in experiments of ordinary metals. So you can see these derivations in more details in our textbook, say Flansburgh or Kittel's second book, or David Pine's lecture notes. So this is the standard, electron-phonon coupling in solids, especially in metals. I believe if you Google this term, CoAnomaly, you should find the history of this term. I think it's back to the 1960s. So let me check. Yes, 1959 by Walter Kohn. So I believe Walter Kohn received a Nobel Prize. By the way, this Walter Kohn is a very famous chemist and also physicist. He actually invented a very useful technique in solid-state physics called density functional theory. So if you are a theorist, you should know this name. He's a big guy in both physics and chemistry community. He got the Nobel Prize in chemistry in 1998. So this is a very good lesson in the era of quantum mechanics, starting in the early 20th century until the end of 20th century. If you live during that period of time, you have a great chance to discover many new things, both in chemistry and also in physics. And I think Walter Kohn is among one of them. Okay, so he is very influential in both physics and chemistry community. So this density functional theory is sometimes called Kohn-Sham theory. And there's another physicist called Sham and Walter Kohn, and they both invented such a numerical approach to solving for this many-body wave function in solid state, which I already mentioned in the very beginning of this course, that it is impossible to solve all the electron wave function, eigenfunctions in solid state material, because it is not possible to solve all this 10 to the 23rd that many coupled Schrödinger equations. But I think Walter Sham and this density functional theory allows one to get the approximated electron wave functions. So they made some approximations through this so-called density functional approach, which allows us to really approximately obtain this many electron eigenstate with the eigenfunctions. Of course, it's not the exact solution, but it's very useful solutions. And you could compare this density functional predictions with the experimental results, and they match in many aspects. So let's just look at this CoAnomaly. So as I mentioned, this derivative is new phonon frequency when Q star goes to 2kF. So let's just look at this. It's a cartoon picture to illustrate this physics, because this CoAnomaly involves both electron and phonons, part of the Hamiltonian by this electron-phonon coupling. Okay? So you can see very clearly that when the momentum transfer between two electrons goes like 2kF, then there's a singularity. So it must happen near the Fermi surface, and it must involve electron-phonon coupling. So let's look at this naive pictures of a free electron Fermi surface, or this dispersion of the free electron particles. So you could roughly consider this partially filled electron band with a quadratic dispersion as almost free electron states, right? Okay. Of course, we know that this is not the exact, but it's used for approximation, and it is a reasonable approximation. And we know very well that those electron states that are very close to the Fermi surface, plus or minus kF. Remember, this is a sphere, right? This is a sphere in a three-dimensional system, the Fermi sphere. And the Fermi momentum or Fermi wave vector could actually point to any directions in the three-dimensional Fermi sphere, right? So I only project this dispersion in this one-dimensional plot like this, but this cartoon picture really suggests that these electrons near the Fermi surface, all around this Fermi surface of the sphere, Fermi sphere, participate this kind of low temperature, low energy excitations. And in particular, remember, so whether this electron absorbed or emit the phonon, it doesn't matter. It just tells us that when Q, which is the difference between the incoming and outgoing electron, K and K prime, is close to 2kF, and that divergence or singularities occurs. But when does that happen? So for electron states, say K and K prime, that are just scattered around these Fermi spheres at the surface of the Fermi sphere, and both K vector with magnitude very close to kF and K prime vector is also very close to the Fermi surface with the magnitudes kF. So both K and K prime vectors have a magnitude that is very close to kF. But then the difference between these two is 2kF. Okay, so you tell me, when does that happen? When both K and K prime are living on the surface of the Fermi sphere, but there are the vectors that, if you take the subtraction between one vector, say K, and another, say K prime, you get 2kF. When does that happen? If you look at this plot, you will know the answer. But I would rather you figure that out, because you are able to figure that out right now. Just tell me what is the value of K and what is the value of K prime, or the relationship between these two. So when vector K is almost minus K prime, and they are very close to the Fermi surface, this is precisely this 2 point right here. Suppose this is K and this is minus K. But both vectors are living on the surface of the Fermi sphere with a minus sign in difference, right? When they differ by a minus sign, then K minus K prime is going to be plus or minus K 2kF. Is that right? Understand? So, which means that the electrons that involve this CoAnomaly must come from the opposite side of the Fermi surface. The opposite side of the Fermi surface. One electron comes from say, the plus sign, positive branch of the momentum, another electron should come from the negative side. So I don't care which comes from where, but I only care that both are the opposite side of the Fermi surface. Okay? So it could be, say, K from here and K prime from there. It could be all the other possibilities. So you can imagine that these processes could cover all the Fermi surface as long as I can find a pair across the Fermi surface along the other side of the Fermi surface, and these pairs always exist, right? You can always find a pair, okay? And therefore, when you sum over this momentum, you sum over all electron states which have another pair across the Fermi surface, and then this will give you a huge accumulation of the divergence in the denominator, right? If you sum over K, which means that you sum over all pairs, there are almost infinite number of electrons in the Fermi surface for realistic materials. So when you sum over all such electron pairs across the Fermi surface, and then all such terms involve the divergence, because the denominator is always very, very small and close to zero, and therefore you get a huge divergence. So let's look at the correspondence between this Coulomb anomaly and electron Fermi surface one more time, because that's very important. So as I mentioned, the electrons across the other side of the Fermi surface, they could interact with each other by electron-phonon. And how would they interact? Well, of course, they do something like this. Okay, so the electrons here and there, they actually coupled by electron-phonon, and they exchange 2kF momentum. So let me just draw a contour picture here. So suppose K prime is minus K. And as a result, Q is actually 2kF, right? So Q is actually 2kF, which is K minus K prime, and K prime is minus K, and therefore Q is 2kF. So this 2kF scattering involves the electrons on both sides of the Fermi surface, on the opposite side of the Fermi surface, and they exchange a phonon with a momentum Q, which is 2kF. And as a result, you will see this Coulomb anomaly in the phonon frequency or phonon dispersion, and you will see this very sharp singular behaviors like this. Suppose this is the edge of the phonon band, but when Q is actually 2kF, the derivative is actually infinity, and you will see the singularity like this. Okay? And this is exactly what experimentalists have seen. Observe this Coulomb anomaly. So which means that the electrons with a 2kF momentum transfer is very efficient scattering for electron and phonon. And experimentalists have observed such a behavior across many different materials at low temperatures. By looking at this phonon dispersion, and I have already introduced to you how to observe phonon dispersion, right? By say neutron scattering, right? And then we can see a sharp edge or a sharp this point right at 2kF, and you know what this kF is for particular metals. You simply just compare the periodic table of this Fermi momentum for a particular metal, and then you know what this 2kF is. And this sharp singular point right at 2kF matches that kF of a particular material, which makes things bingo, right? So when you find such a bingo phenomena, you'll get very excited because if you don't know this scattering, you don't know where it comes from, you just know this phenomena. But since you know such an electron-phonon coupling, which is very efficient scattering at the 2kF transfer, and then you realize that this is due to electron-phonon coupling. Okay, so this kind of a CoAnomaly is very, very important even today. Okay, so it is a very important mechanism for the charge density wave or CDW states, in some novel two-dimensional materials, such as tantalum disulfide, TS2, or other graphene-like 2D material. And of course, graphene doesn't have such a CDW, but there are many strongly correlated systems that live in this two-dimensional surface, and they have such a strong CoAnomaly, which make this electronic states unstable, and they tend to form a charge density wave pattern like this. So you will see some bright spots when you measure the charge density on the surface of such materials by STM. So you know STM, right? Standing tunneling microscope, right? So, and you could very clearly see such a Davy star-like pattern where more charged particles accumulated on the vertex of this Davy star, and less electrons are accumulated elsewhere. And this is actually a periodic pattern of your electron charges at the surface of this 2D material. And the reason why they form such a charge density wave state is precisely because of the CoAnomaly, that electron-phonon coupling could actually change the electronic state in such a way that they form kind of periodic modulations over space. So the CoAnomaly is a very important solid-state phenomena that everyone should know. Okay, so you may just have heard such a term when you studied, introduction of solid-state physics, without knowing the underlying physics, but now you know why we have such a CoAnomaly. So as I mentioned, everything that we introduce here is related to both theory and experiments. Okay, the reason why we have such a phenomena is because of electron-phonon coupling, and the reason why we study this is because this is a real phenomena, and you understand why this phenomena occurs by now. So let's look at another aspect, which is the electron energy and mass enhancement, say via electron-phonon. So as I mentioned, the electron-phonon coupling affects both electronic state and phonon state. Okay, so we just discussed the CoAnomaly from the phonon spectrum. So now let's look at the electron energy. And both energies are coming from the same expression, which is this one. Remember the general term, which involves both Fermi function and the Bose factor. So let's look at the electronic part of the correction. And to do so, we fix at zero temperature, and therefore the Bose factor vanishes. Okay, remember, if you don't have the Bose-Einstein condensation, just the excited state bosons, and the boson occupation is actually zero at zero temperature. Okay, for phonon, it is the case. And therefore, only the second term survives, because the first term vanishes. To actually isolate this electronic part of energy corrections, we need to do so. Okay, otherwise, at finite temperatures, this both NQ and NK contribute, and it's a bit messy. But we can simplify this by considering only the zero temperature contributions. So the electron energy could be evaluated in a similar manner that we could take the derivatives, this total energy with respect to this electron occupation. We get the free electron kinetic energy plus the electron phonon contributions and minus nk prime. Okay, so we may not have time to finish this. Let's just stop here for now. Okay, so in a similar way, we could calculate the corrected electron energies due to the electron-phonon coupling, and the additional term that comes from the electron-phonon coupling is this summation over k prime, and there are two contributions which will be discussed on Wednesday. All right, and so you will see that there are two contributions. One exists always, meaning for both insulator and a metal. Another term exists only for metal. So, which means that this phenomena is there for everyone, for all the materials. But for metallic materials, there is a additional term, and we will analyze these two terms on Wednesday. Okay, so I guess that's about it today. Okay, so I encourage you to read and derive these expressions by yourself, and all these equations could be found in our references, and it is a standard, solid state knowledge that you should know. Okay, and next time we will address this electron mass enhancement by electron-phonon coupling, and a phenomenon or term called polaron. And the concept of electron mass enhancement will be introduced, which is, again, a very important concept. Whether you are a series or experimentalist, doesn't matter. So you have to know the concept of electron mass enhancement. So how can electron mass get enhanced? So the short answer is that they interact with the other particles, such as electron-phonon coupling, will effectively enhance the electron mass. And this mass enhancement of electrons could also be detected and observed in experiments. So again, it is a real phenomenon. So everything that we introduce here have been observed in experiments. So in other words, this is a real thing. Okay, so let's call it a day today. And remember, finish your homework as soon as possible.